There's a reason why the electronics assembly industry is changing from tin lead solder to lead-free solder alloys. In the 1970s, lead had become commonly recognized as a potential health hazard and was eliminated from gasoline and paint. In addition, household plumbing has been changing from lead to no lead. As part of the continuing effort to reduce the potential for environmental issues with the lead contained in tin solders, there is now momentum for using lead-free solder in the electronics industry. The main reason for this momentum is that European countries have a legal mandate to change to lead-free soldering processes by July 1, 2006. Japan is also committed to this timetable. Given the global market commitment to lead-free electronics, the United States is preparing to do the same. The question isn't whether the switch will be made to lead-free solder throughout our industry, but when. Everyone agrees that it's just a matter of time when lead will be banned and removed from all electronic products. The switch to lead-free solder will keep lead out of our landfills and from being burned in our incinerators, which has a potential benefit for our environment. Lead is toxic and can severely affect our central nervous systems. Ingestion is one of the most likely routes of entry while performing electronics assembly. Using proper precautions, we've learned how to minimize the potential hazards of tin lead solder. We already know that lead can be ingested by touching food, cigarettes, chewing tobacco, or makeup after handling tin lead solder, solder paste, or soldered boards without hand protection. And we also know that the hazard can be avoided by washing our hands with soap and water before touching any item that will come into contact with our mouths. What this means is that we can protect ourselves in the workplace. But the situation involving lead is not so clear when we discard our old electronic products. Our landfills contain tons of electronic components and circuit boards that were manufactured and assembled using tin lead solder. There is concern that the lead in the landfills will end up in the water table by leaching. Now that you know why many companies are switching to lead-free soldering processes, let's take a look at the different types of lead-free solder alloys. There are many types of lead-free solders available today. In fact, the tin-silver alloy has been used for many years in higher melting point applications. The melting point for this lead-free alloy is about 40 degrees C higher than tin lead solder, which becomes liquid at 183 degrees C. This means that there's more potential for heat damage to the circuit board and components during assembly. The most common lead-free alloy is tin-silver copper. There are a number of formulations that may be used for hand soldering rework. The variations involve the percentages of silver and copper. A commonly used alloy contains 96.5% tin, 3% silver, and 0.5% copper. Tin-silver copper has a melting point of about 217 degrees C. A variation of this alloy is also used for reflow soldering. Another lead-free alloy is tin copper, a less expensive compound proposed for use in lead-free wave soldering applications due to cost considerations. The melting point of tin copper is somewhat higher at 227 degrees C. Your company will have already selected the specific lead-free soldering alloy it will be using for its soldering applications. It's important to become familiar with the basic characteristics of lead-free solders. These alloys tend to have a higher surface tension, meaning they don't spread along the surface of the connection as well as their tin lead counterparts. As stated previously, the melting temperatures are up to 40 degrees C higher than tin lead. For example, a reflow temperature for a lead-free process may be 235 to 260 degrees C versus 205 to 220 degrees C for tin lead. Although studies have indicated that lead-free solder joints can be as reliable as tin lead, there are a number of considerations in implementing the process. Here are some things to be aware of. Components and circuit boards need to be able to withstand the higher soldering temperatures. Also, because of these higher temperatures, the requirement for baking moisture-sensitive components and circuit board materials becomes even more important. When moisture is retained in these types of devices and they undergo higher processing temperatures, there may be potential for board or component delamination. Solder defects may also increase due to poor or reduced wetting and may create more rework. Fluxes will need to clean surfaces more aggressively due to the reduced spreading of the lead-free solder and will need to function properly at higher soldering temperatures because there's more possibility of oxidation and potentially longer soldering times at the higher temperature. If we move to more active fluxes, they may require a more thorough cleaning process to remove the more aggressive and possibly still active flux residues. Finally, the solder joints may have a different appearance, depending on the lead-free alloy used. Visual inspection criteria for lead-free and tin lead solder joints are referred to in IPC A610D. There are two basic types of rework. The first involves removing the component, preparing the lands, then repositioning and resoldering the component. The second involves simply touching up a solder connection that doesn't meet quality and reliability standards. We'll discuss component removal and replacement first. There are a number of ways to remove a component, prepare the lands, and to resolder the connections. The method you'll choose has to do with the type of component being reworked and your company's policy. For a comprehensive demonstration of the various techniques available, please refer to IPC's Surface Mount Rework series, as well as our training DVD on rework stations. This video will concentrate on the differences between tin lead and lead-free rework processes, and we won't get into each of the soldering processes for removing and replacing components. Component removal is pretty much the same whether you're reworking a tin lead solder joint or a connection made with a lead-free alloy. The main difference is the amount of heat you'll need to melt the solder joints. The lead-free alloys require a higher temperature. When using higher soldering temperatures, it can be helpful to preheat the assembly. If component removal is done at room temperature, there is a greater possibility that the board may be burned. Let's watch a common technique for removing an SOIC component using a soldering iron fitted with a special tip. Before beginning, it's important to clean and tin the tip of the iron. Now, place the tip over the component. Once all the solder joints have melted, lift the iron and remove the component. Then set the hot component on a heat-resistant surface until it cools down. Let's watch another component removal procedure using hot air. At this point, the solder that remains on the lands needs to be removed so that the component can be properly repositioned and resoldered. Land preparation is typically done with a solder braid. Again, higher soldering temperatures are used to wick the lead-free solder onto the braid. Using a compatible external flux will improve the wetting characteristics and allow the solder to wick onto the braid quicker. This decreases the possibility of thermal damage to the circuit board. Another method is using continuous vacuum extraction. After the tip heats up, we'll apply a light coating of solder right on the tip. Again, you may also want to apply an external flux over all of the lands. Both of these steps will help speed up the heat transfer process. Now we position the flat end of the tip over the first few lands. The vacuum should now be activated and allowed to run on a continuous basis. The surge of air through the orifice will tend to cool the tip. One advantage of the larger tips is they can maintain their operating temperature better than the thinner tips, since there is a larger mass through which the heat is transferred. Notice how we move the tip along the length of the lands to remove all of the solder. It's very important not to put any downward pressure on the lands. Once the solder has been removed from the lands, any flux residue should be cleaned. Now we'll reposition and solder the component. You can use a tweezer or vacuum pickup tool to pick up and position this SOIC component. You can usually position an SOIC component onto the lands without the aid of a microscope. Just make sure that all of the leads are centered evenly from side to side. You'll also need to make sure that the heel and toe of each lead is centered evenly in the lengthwise direction. Tip selection will be based on the width of the component leads. If a chisel tip will fit, it will transfer heat faster than a conical tip. The selection of the solder wire will also depend on the width of the leads. For this example, we'll be using a tin silver copper alloy that has a melting temperature of 217 degrees C. Now we're ready to tack the component in position. It's helpful to hold the component down with tweezers or a wooden stick so that it doesn't move when you tack two of the corners. A common method of tacking the corners is to add a very small amount of solder to the tip and then touch the tip to the junction between the land and the lead. At this point, we're ready for the soldering process. To improve wetting, it's usually a good idea to add a compatible type of external flux, even though there is already some flux in the core of the solder wire. We begin by resting the tip flush against the top of the lead. Now, contact the lead and the land with the solder wire, away from the tip. This will allow the flux to clean the connection instead of burning away on the tip of the iron. You don't want to press down on the leads or the lands. Even light pressure can bend or skew the lead out of position or damage the land. You can proceed from one joint to the next until all the joints are soldered. An alternate method is to place the solder wire on the land and then contact the wire with the tip of the iron. This procedure is designed to minimize the amount of time that the iron is in contact with the joint. Considering the higher melting temperatures for lead-free solders, some companies prefer this method to slightly shorten soldering times. After all of the joints are soldered, we'll need to clean the flux residues, unless you are using a no-clean flux. Your company will provide you with a compatible cleaning solution. A brush can access between the leads and around the component, but you need to be careful not to bend the leads with excessive force. There will also be flux residues underneath the component that you may not be able to remove by hand. Reworked assemblies can also be processed through a cleaning machine to remove these hidden residues. Now we'll inspect these joints to make sure they look right. Notice that the tin silver copper alloy is grainier in appearance than the tin lead solder joints you're used to seeing. This graininess is caused by the higher soldering temperatures and is generally considered a cosmetic issue. We'll discuss lead-free solder joint evaluation more thoroughly in Section 3. A faster method of hand soldering rework is by what's known as drag soldering. Although drag soldering is an excellent technique to use during tin lead solder rework, it is much more difficult to accomplish successfully with the lead-free alloys. One method for increasing the probability of a positive outcome when drag soldering in a lead-free process is to preheat the assembly. Preheating will improve the wetting of the solder. But even when we preheat, there will be the occasional solder bridge. Solder bridges can be fixed by adding flux and drawing off the excess solder onto the tip of the iron. The choice then becomes whether to fix the solder bridges one at a time or to solder the leads one at a time. Some find that by preheating the assembly, drag soldering is faster than point-to-point soldering, even when you factor in repairing a solder bridge or two. Our last topic in this section involves touching up unacceptable solder connections. The most important consideration is using compatible lead-free solder and flux, and setting the soldering temperature for the higher lead-free alloy melting temperature. Whenever a solder joint is rejected for insufficient solder, you'll need to add a small amount of solder to touch up the joint. To repair a solder bridge, first add flux, then position a clean solderless tip on top of the bridged leads and reheat the joints completely. When you remove the tip, the excess solder will follow the heat source. Make sure to always melt both of the solder connections completely during the bridge removal procedure to avoid creating differences in the internal structure of the solder joints. This final section involves the visual inspection of lead-free solder joints. We'll be examining the attributes of a typical lead-free connection for chip, gull wing, and J-lead components, and comparing these lead-free joints with their tin lead counterparts. That's so you'll be aware of what to expect when evaluating lead-free connections. We'll also be looking at some of the variations that may or may not be acceptable. This is a good example of a preferred or target rectangular chip component using tin silver copper solder. Notice how the solder feathers onto the land and up onto the termination. The solder fillet is curved inward or concave. The solder covers all of the land and the termination. The texture is a little bit grainy. The outline of the termination is visible beneath the solder. The amount of solder here is just about perfect. Notice the difference in appearance between this solder joint and the tin lead solder connections that you're used to seeing. Here are examples of target gull wing and J-lead solder joints. Again, let's compare them with their tin lead counterparts. Here's another chip component with a little bit less solder. You can see that there is still some graininess, and the coverage is even. The fillet is concave. This solder joint is perfectly acceptable, even though there is less solder in the connection. Now here's another one with quite a bit more solder. The important thing to notice is the angle of contact between the solder and the metal. Proper wetting is indicated by a solder contact angle that does not exceed 90 degrees, which is a square or right angle. The lower the contact angle, the better the wetting. As you can see, there is a range of acceptable solder joints. You will be expected to know an acceptable solder joint from a defective one before you begin evaluating surface mount lead-free connections. The requirements for acceptable tin lead and lead-free solder joints are referred to in the IPC A610D standard. Now let's look at some solder joints that are less than ideal. Here are some examples of non-wetting. Notice that the solder has not adhered to either the termination or land. Non-wetting will occur if the reflow or wave soldering temperature is too low or there is poor flux activity. Incomplete reflow occurs when insufficient heat is applied to the assembly during the soldering operation. This means the solder paste may not have properly wetted the surfaces to be soldered and will not form an acceptable electrical and mechanical connection. Tombstoning is a defect that is specific to chip components. Notice how one end of the component termination is completely lifted off the land. This joint has excessive solder. The fillet is not concave and there is solder flowing over the edge of the land. Too much solder paste was deposited on this land, and it is not possible to tell whether proper wetting has occurred. This condition is called solder bridging. A bridge is an electrical path or short circuit that was not intended. And these are solder balls. They can create electrical shorts by lodging in between two conductors or component leads. There are several types of cosmetic imperfections, such as fillet lifting, cooling lines, and tears that are more likely to occur in a lead-free process. It's important to understand that these types of conditions typically won't affect the strength of the mechanical and electrical connection of the solder joint. Although some of these conditions are always unacceptable, many of these imperfections can be allowed, in various degrees, depending on what type of product they would be used in. For example, we'd all expect that any aircraft or medical electronics would be highly reliable. But we may be able to live with some minor cosmetic imperfections in a portable CD player as long as the product works. The IPC A610 has 3 classes of requirements based on the final use of the end product. Class 1 is for consumer products. Class 2 is for business and computer products. And Class 3 is for high reliability electronics, where failure is not an option. The specification and the class of requirements that your company uses to inspect solder joints will be clearly explained to you. Some companies build a wide range of products with different requirements. Other companies build only one class of product. Part of your job is to make sure to always apply the right criteria to each assembly. This program has presented the essential information required to successfully use lead-free solder alloys in surface mount rework operations. We discussed the reason for the switch to lead-free and the characteristics of the specific alloys. Then we showed what's involved in lead-free hand soldering rework for surface mount components. And we concluded with a brief explanation of the acceptance criteria used to evaluate lead-free surface mount solder joints. The more time you spend working with and observing the results of lead-free alloys, the more confident you'll become about implementing and evaluating reliable solder joints. And you'll be helping the environment too.